All right, we started section 4.2 last time. We talked about prime and composite numbers. Just as a reminder, prime numbers are positive integers with exactly two factors, so themselves and one. And one is not a prime number because it only has one factor. And then composite numbers have more than two factors, like the example of 4. It's divisible by 1, 2, and 4. And so that's called a composite number. And again, 1 doesn't fit into that category either. So 1 is neither prime nor composite. Neither are any of your negatives or 0 because these are only positive numbers we're dealing with. We talked about some prime factorization. I showed you how to do a couple of methods for just a basic, like, whole number given to you in its sort of standard form. And we looked at doing both a tree, factor tree, and we looked at doing like this division algorithm steps where it puts things in nice orders. We did one where it was in partially factored form. We talked about the fact that it is highly unhelpful to multiply that back out first. It would be not helpful at all. So instead we just continue the factoring on and use properties of exponents. And then we talked about one where it looked like we had some pieces in common and we had some addition between them. And we did some algebra kind of factoring where we pulled things out in front that were common to both pieces, put the pieces that were left, and consolidated. So we're going to actually take a look today at the fundamental theorem of arithmetic. Anytime somebody uses the words fundamental theorem, it means it's really important. And this theorem says each composite number, we just defined that, can be written as a product of primes in one and only one way, except for the order of the primes. So for example, if you had we'll do a very simple example here. We'll do the number 12. So if we break down a 12, it's 4 and 3, or you could do 2 and 6 if you prefer, and you get 2, 2, and 3. So the number 12 is 2 times 2 times 3, and there is no other prime factorization for this number unless you just like shift the 2's and the 3's around. But that's not what we're talking about. Okay, except for the order of things, there's one and only one prime factorization. Got a few more theorems. The next theorem actually talks about the fact that divisors come in pairs. And we've encountered this even today because somebody asked a question about the number 28. So when we encountered the number 28, I said, I find it easier to remember all the factors if I put them in pairs. Well, factors always come in pairs. So if you have a divisor d of n, then n divided by d is a factor as well. It's the pair that multiplies together to get back n. So for example, we'll just use the 28 that you guys mentioned from before. If 2 divides 28, which of course it does, then 28 divided by 2, which is 14, 14 will divide 28. So these are the pairs that go together. So once you have 1, you automatically get 2. Now they may not be unique, right? Like if you looked at the number 4 and you say, hey, 2 divides 4, well, 4 divided by 2 is also 2, and so it's just the same piece. So it doesn't necessarily create a unique factor pair, but it does create the pair with it. Sometimes we're looking to see if a number is prime or composite, and it may not be readily obvious to us if it's large enough, right? So if I gave you the number 433, you might be like, well, I'm not sure. It's not odd. I mean, it's not even, so I don't know for sure that it works, but it's big enough that it feels like maybe something's going to go into it, right? You all know what I'm talking about, yeah? Well, the question becomes, if I'm looking at divisors like Rylan, the one that you did today where you looked at 13 and then you looked at 17, you looked at 19, at some point you have to wonder, well, how high do I divide before I decide it doesn't work anymore, right? Because if 13 and 17 and 19 on that one had not divided the 209, well, we would have gone to the next one, like 21, and that might not have worked. And then we would have said, okay, well, maybe 23. When do you get to stop? When do you get to decide, yep, it's prime? Well, that's what the next theorem addresses. It actually says that if you do have a composite number, then it will have a prime factor whose square is less than or equal to the number. Now, that sounds a little bit awkward, but Theorem 416 goes with it. If n is a whole number greater than 1 and it's not divisible by any prime, right? when do I stop kind of question. Such that p squared is less than or equal to n, then n is prime. So here's the way it works. I think I created 433, right? So we're just going to use 433 as an example. So if you take the square root of 433, grab your calculator, figure it out what it is. It's going to be, I assume it's not going to be a perfect square. Oh yeah, it's good and ugly. So it's approximately 20.8 if I use one decimal. What this tells you is that if it's divisible by something at all, besides 1, the number it's divisible by is smaller than 20.8. You don't have to go very far at all, do you? There's only a few prime numbers between 1 and 20 that you'd actually have to test before you could say, yep, it's prime. Or, oh, look, I found it. That's good news. And that's what this theorem tells us, is it tells us sort of the upper end of where I can stop trying to test numbers. So our example number 2 is just this. It says, what is the greatest prime you would have to consider when you're looking at the number 967? So we do the same thing that I was alluding to here with 433. We take the square root. So the square root of 967. And let's write an approximation for it, and then we'll actually answer the question, because the answer is not the approximate. That's not what the answer is to this question. If you take the square root of 967, you get approximately 31.1. Is that okay? Calculator good with that? Okay, great. What we want to know is we want to know the biggest prime number smaller than 31.1. So what is the biggest prime number smaller than that? 29. Is 31 prime though? I think 31 is as well. Now it's not likely to be 31 because it's so close already to the value, but 31 would be our answer for this. 31 is the biggest number that we would test. This is the last prime. If we had this same question with the number that I had over here where I had 20.8, it wouldn't be 20, right? Even though it's approximately 20 because 20 is not prime. Here we would actually have to test 19 as our last one. Is that all right? Okay. So it's not just the biggest number smaller, whole number. It's the biggest prime that's smaller. So on this one it would be 19. On this one it's actually 31. Example 3 is kind of interesting. It's kind of a part C kind of question. It says to show that if the number 1 were considered a prime, because lots of people want it to be prime. I've argued with students about the fact that it's not prime by definition before. And the reality is you don't want it to be prime. So if 1 were considered prime, then every number would have more than one prime factorization. So I'm going to use that same example I had before because we already did it, 12. And we found that the prime factorization was 2 times 2 times 3. And you all nodded your heads and were like, yeah, that's good, right? That's my prime factorization. Well, the problem here is that if the number 1 were considered a prime number, then we would also have this as a prime factorization. It's a true fact, right? And if 1 were prime, we could put it on there and it'd be another prime factorization for this, but it gets worse. Because not only would that be true, but so would this. And so would this. And this is a problem. We don't want there to be lots of prime factorizations for numbers. We don't want 1 to be considered prime because it destroys the fundamental principle, or fundamental theorem, of arithmetic. If 1 were prime, the fundamental principle of arithmetic wouldn't work. It would be false. So that's a problem. Example 4. Mr. Arbor wants to plant apple trees in a rectangular array. If he has 36 saplings, find all possible numbers of rows if each row is to have the same number of trees. So I will start you out with an example. We could have one row of 36 trees. Or if you prefer, we could say we have 36 rows of one tree. What's another rectangular array that's a little more interesting than one strong, long line of trees?
2 rows with 13 trees.
Close. 2 rows with not 13, but 18. Yeah, 18 trees. You're thinking of 26. 2 rows of 18 trees, or you could say 18 rows of 2 trees. That's the same thing. So I'm not going to write them all out every time. But yeah, 2 rows of 18 trees. What else could you have? 3 rows of 12. 4 and 9.
6 and 6.
Yep. And what you're really looking for as you did that process was factor pairs, weren't you? You are. And if you're careful as you do this and you go up, sequentially with every value that divides it, eventually what happens is that your last row has nothing in between that divides. Now this one actually matched. It was 6 and 6. That might not happen. You might have numbers that are further apart, like 4 and 6 at the end, but 5 doesn't divide and it's the only number in between. So you've captured them all because you've done them in an organized way. Any questions on that? Okay, last question for today. Bob says that to check whether a number is prime, he just uses divisibility rules he knows for 2, 3, 4, 5, 6, 8, 10. He says if a number is not divisible by these numbers, then it's prime. How do you respond? Okay, so let me kind of put that in a more general term with I'll use your 209 as an example though. Some numbers like 209 don't divide by these values. But 11, did you say it was 11 and 19? 11 divides 209, and 19 divides 209. So 209 is not prime. But it didn't divide by anything he tried, or would have tried, right? So one of the problems that his method is going to have is that it's not going to actually catch all the prime numbers. There are some prime numbers that are just not going to be, adequately, accounted for. There's other numbers that are actually going to be overkill, there's another problem with this is that it's going to be overkill for some numbers. For example, if 2 does not divide a number, I've mentioned this before, then there is no need to test if any other even number works. The list that he gave in particular, that would include 4, 6, 8, and 10. So there are some things, if you tested all of these numbers, that would be wasting your time. the number 2 did not divide it, there is absolutely no need to test 4, 6, 8, or 10 divides. It's not going to work, right? So in some ways, it fails because it's not comprehensive enough, right, like with 209. And in some ways, it fails because it's unnecessary computations. It's busy work as well. Does that make sense?